In section 6.2, we want to talk about a very special discrete probability distribution known as the binomial probability distribution. Now, the binomial probability distribution actually has a special formula that will find the probabilities for us, which is very nice. It also provides the mathematical foundation for some surveys and polling data that we'll be able to work with in chapters 9, 10, well, actually 8, 9, 10, 11, which I actually mentioned right down here at the bottom of the box. So it provides that math foundation for chapters 8 through 11. So it's an important idea that we really want to make sure we understand. Now, the thing about this special formula that will find probabilities for us is that it only works if we know the criteria for the binomial probability experiment. It only works in special cases. And I believe this was all figured out by Jacob Bernoulli, actually the same person that also figured out expected value. He was very big into the discrete probability distributions. What can I tell you? All right, so the criteria for a binomial probability experiment will be number one, the random probability experiment is performed a fixed number of times n. Each repetition of the experiment is called a trial. Those trials are independent. For each trial, there are two disjoint outcomes, success or failure. And x is the number of successes in those n trials. Notice you can have as little as 0 successes and then 1 success, 2 successes, 3 successes, all the way up to n successes, where n is the number of trials that you have. So if you have 10 trials, you could have 10 successes, hypothetically speaking. And the probability of success is consistent for each trial of the experiment. So P is the probability of success, and Q is the complement of that, which is the probability of failure. So it's 1 minus P. Now, a couple things to note. N, P, and Q are numbers. S, F, and X are words. And success is not a good thing or a bad thing. We, of course, in English usually use success to mean good things, right? But that is not the case here. When Bernoulli was first inventing these ideas, he was not necessarily thinking of it as good or bad. It just is what you're looking for. So just keep that in mind. Now, if you're thinking, oh, I'm going to have to write all of this onto my exam notes packet, no, you will not, because it's already there for you. It's all right here, right, into the exam notes packet. So it's all written down for you. So you just have to know what you're looking at. But never forget that success and failure is based on perspective. It's not a good or a bad thing. It just is what it is. Now, if you're thinking, well, that was a lot of confusing stuff, it'll help when we go through an example. So let's do one, shall we? So you're going to pretend it's you, a student takes a multiple choice test that has 10 questions. Each question has 5 choices, only one of which is correct. The student just guesses randomly at each answer. This is one of my nightmares. You show up for a test and you have no idea what's going on, so you just randomly guess. I've had bad dreams about this. Explain how this experiment is binomial and identify N, P, Q, S, F, and X. Okay, so let's see here. Let's start off with number 1. Was there a fixed number of trials? When the student takes this particular quiz, the number of trials is fixed at 10 questions. So there's a fixed number of trials, sure. It's n equals 10 questions. So for us, the trials are questions. That'll change from problem to problem. In this particular problem, it's 10 questions. That's your n. All right, number 2, the trials are independent. Well, sure, right? So, what you guess on one thing has no effect on the guess on the next thing. And because the student is guessing randomly, which of course you would never want to do on an actual test, then every choice, if whether they got one right or one wrong, has no effect on the next question. So each question has no effect on the next question, which of course is a dangerous thing. That's why you always want to study and go to class, because you never know when you're going to be given a pop quiz, right? So each question has no effect on the next question, which is a little bit obvious. All right, number 3. This is the good one. Success and failure, right? So there has to be 2 disjoint outcomes, right? No overlap. Success and failure. All right, so 2 disjoint outcomes. And we'll say what they are. S and F and X are in words. So we'll say S and F. S is success, which was guessing correctly, I would imagine. So guess correctly. We'll make it a good thing in this case. And then this will be guess wrong, right? I guess I could just say correct or wrong because the guess is implied in the whole problem anyway. And notice by framing it this way, we're putting ourselves on the student's side. We're looking for them to succeed. We're looking for them to be correct. Now, putting these two things together, X is the number of successes in N trials. Well, let's put that in context. That's the number correct out of N, which was 10, trials, which is questions. And you'll note the student can get as few as 0 correct all the way up to, hypothetically speaking, they could get all 10 correct. But since they're randomly guessing, I doubt that's going to happen. All right, so we've got N right here. Actually, let me underline these in pink so you can see them. N's right there, S is right there, F is right there, X is all of this. All right, now last bit is the probability of success and failure. I guess are the probabilities of success and failure consistent? So probability consistent, right? Does it stay the same from trial to trial? Well, since the student's randomly guessing, sure, right? So the probability of success is lowercase p. P is the probability of success, which is the probability of correct. All right, now for that, you have to go back and read the problem again. And it says each question has 5 choices, only one of which is correct. So the probability of getting one right is 1 out of 5. You're basically choosing between an A, B, C, D, E multiple choice question, right? So what's the probability of failure, which is Q? Get it? P, Q. They're right after each other in the alphabet. Mind your P's and Q's. So the probability of failure is 1 minus 1/5, which is 4/5. If you have 1 out of 5 that's a correct choice, then 4 out of 5 are wrong choices. And these are the same for every question. So they're consistent. That's what this consistent means, the same. And so we have all the criteria. Its probabilities of success and failure are consistent. There's only 2 disjoint outcomes, success and failure, which are correct and wrong. Every choice is independent, and that's because the student is randomly guessing, right? A lot of this is based on the fact that the student is randomly guessing. That's important for most of this, right? Because they're randomly guessing, everything's independent of each other, and the probabilities are consistent because they have no idea what they're guessing, right? All right. Because student is randomly guessing, right? They don't know anything of what's going on. They're not trying to get it from context. They're not trying to remember it from class. They're just randomly guessing, and so therefore these never change. Of course, this is not entirely how a real test would be taken, because hopefully you've shown up for class at some point, but nevertheless, it'll work for us. And of course, the fixed number of trials we have. So we have all of those things. And again, this is because the student is randomly guessing up here. And again, that's not really fair. In real life, you would get clues from one guess to the next guess or things like that. But we're going to pretend that the student's completely randomly guessing for all of these things. And hopefully this helps you see the criteria for a binomial experiment. It's actually an experiment we hit those criteria pretty regularly in later chapters, chapters 8 through 11, particularly for surveys and polling people. So let's keep going and see if we can apply it to this next problem, see if we really understand these criteria. So for example 2, we want to see if these are binomial. If they are, we want to find N, P, Q, S, F, and X. And if not, explain why not. So we have a loaded die that has all 6 numbers, but it's weighted in such a way that it tosses the number 2 75% of the time. We toss the die and record the number of rolls it takes to obtain a 2. I think we're in trouble right off the bat. Right here, you record the number of rolls it takes. So it didn't say toss this die 7 times. It says record the number of rolls. So you could keep tossing and tossing and tossing, or you could get it right off the bat on the first toss. So this is not binomial because the number of trials is not fixed. All right. Now, according to a 2017 biomedical research paper, 81% of people who have coronary bypass surgery are over age 60. 20 random coronary bypass patients are sampled, and the number who are over 60 is recorded. Okay, so right here, I'm noticing an N right there with the 20. So I think we've got the first part, right? So in part one, we have a fixed number of trials, and that would be a yes, right? We have that. N is equal to 20, in this case, patients. So our trials are patients this time. And I'll give you a hint, this one's going to work. This one is binomial. So start two, independent. Well, because they're random patients, they're not related to each other. That's the way you would lose independence in this case. So because the patients are random, they'll have no effect on each other. Whether I have bypass surgery and the age I had it at has no effect on anybody else other than people I'm related to, probably. So patients are random, so there's no relation between them. Good, got that one. So independent, check. Step three, this is the big one. We need two disjoint outcomes. And we have it. I'll give it a little check mark. We have success and we have failure. Success, well, you have to look at what they're looking for. They want to know the number that are over 60. See this? Over age 60. So success for us is over 60, which means failure is under 60. And this illustrates my point perfectly. Neither one of these is necessarily a good or bad thing. It's just that's what you were looking for. If the number over 60 is recorded, then over 60 is your success. Period. And then X is developed from these things. X is the number of patients. Oh, I guess I should say the number over 60. I'll write it that way. Out of 20 patients. Right? This part's your success, and this part is your N. Right? There's your N right there. All right, so we have N, S, F, and X. All we need is the probability of success to be consistent, and we're golden. So actually, and the probability of failures to be consistent as well. So probability consistent. And sure enough, they are. Little p is the probability of success, which is the chance of being over 60. And it tells us right here, it's 81%. So this is 0.81. And therefore Q, which is the probability of failure, is the complement of that. So it's 1 minus 0.81, which would be 0.19. And these two are consistent. Right? That just is what it is for the whole population. So we're set. We have P, we have Q, we have S, we have F, well, SF, X, and N. We have all the things that we're being asked for. So this is binomial. All right, last one. You have a jar that contains 5 red marbles, 9 blue marbles, and 6 green marbles. You randomly select 3 marbles from the jar without replacement. The random variable represents the number of red marbles chosen. And I can already see we're in trouble. And we're in trouble right there. We've lost independence, right? Once you're sampling without replacement, you no longer have part 2, the independence. And actually, you don't have consistent probabilities either. That happens because you're losing part 2. So it's not binomial because sampling without replacement, that's chapter 5. We learned in chapter 5 that is not independent. And therefore, this is not a binomial experiment. We can make a note the probability of success and the probability of failure are also not consistent. But that's happening because it's not binomial, or excuse me, it's not independent. Those two things often go together, number 2 and number 4 in the criteria.